So this is page 20 in the Unit P packet. This is the last page of content because everything after this is reference material. So we're continuing the idea of applying the concepts of vectors. So the first example, for a man to cross a lake to a point directly east of his cabin, he must set a course 6 degrees south of due east so as to compensate for a current that flows to the northeast 30 degrees north of due east. If the man's boat travels 20 miles an hour in still water, so basically if there was no current, it would go 20 miles an hour. We'll keep that in mind. What is the rate of the current to the nearest integer? All right. So we can start off with a diagram. Due east, that's easy enough. If I use my line draw tool. All right. So this is the route that he wants to be on. In order to accomplish this, he has to go at an angle 6 degrees south of due east of 60. Geez, I just wanted it to be 60. 6 degrees. All right. There's a current that's going 30 degrees north of due east, so something like that. All right. So the boat travels 20 miles an hour in still water. Okay, well, what that would mean is if he didn't have a current to worry about, that's what the rate of the velocity would be, 20 miles an hour. However, he does have a current to worry about, and that current has a value that is unknown. All right, so we'll call that C. So that'll be my vector C. All right, we need the resultant velocity of the boat, which would be what would get him from the cabin to a point directly east of his cabin. Right, so his cabin's on the left, and this is just some point on the right. All right, so this is where he wants to go. All right. So then we know that in subcapacity, he's going to be aided by the current. All right. Now, the still water value, which I'll call S for still water, they're telling us that value is equal to 20 miles an hour. All right. So what he's doing is he is operating his boat, and it's just kind of a weird way to say it, but they're saying that he's operating his boat at a rate that would normally produce 20 miles per hour in still water, but because there's a current involved, it's gonna lead to a different velocity. All right, and we need to figure out what that is, along with the current itself. All right, so it really is just a question of, all right, well, how long should these vectors be in order to come up with that resultant? And also, and when I say how long should they be, I mean, what is the magnitude of each of these vectors? All right, so I'm going to smidge it down. I'm going to trim some of this. If I take this one, copy it, and bring it over here somewhere, like right about there, what I can do is I can trim the fat, and that tells me that vector C ought to be this long. All right. Vector S ought to be this long, assuming that that vector R is appropriated in length, which really doesn't matter actually. All right, so we got this vector. I'm going to pull this out. I'm going to get rid of this. I'm going to duplicate this. Put it over here. I'm going to move this over. And we'll create a parallelogram out of this. All right, does the diagram have to be perfect? No. Does the diagram even have to exist? Depending on the question. All right, some questions will ask you for a diagram, some won't. All right, so this is what we're up against. So it really is just a matter of finding a vector sum because we're looking for a resultant vector. All right, so vector sum. Specifically, C plus S. All right, at first glance, it does not look like I have a whole heck of a lot of information, but actually, as it turns out, I have a ton. I get an angle, 30 degrees. and I get another angle of 6 degrees, but that's 6 degrees below the axis. All right, so we'll keep that in mind. All right, so we also know the magnitude of S. We don't know the magnitude of C, so we'll have to leave that variable. All right, so when I want to state vector C, I would say magnitude of C, which again is unknown, quality vector symbol, cosine of 30, comma sine of 30, vector S, which I do know is 20, cosine, now it's 6 degrees backwards from 360, so 354 degrees, comma sine of 354 degrees. So we want to add these two together, and that would give us our resultant vector, which is going off in the positive direction, positive x direction, with an unknown value r, but we do know it's going off at the 0 degree angle. All right, so cosine of 0, sine of 0. So from this, I can develop a system of equations. I can say magnitude of C, cosine of 30, plus 20 cosine of 354 degrees is going to be equal to cosine of, well, cosine of 0 is equal to 1 multiplied by magnitude of r is going to be magnitude of r. And the second equation, so basically what I'm doing is I'm distributing the magnitudes to each part, and then I'm just making an equation out of the x components. So now I'm going to make an equation out of the y components after distributing. So magnitude of C times the sine of 30 plus 20 sine of 354 degrees is going to be, well, sine of 0 is 0, so 0. All right. So now I can solve. All right. The second equation is, yeah, it's a system of equations, two variables, but the second equation is, it only contains one variable. So the magnitude of C is going to be equal to, if I subtract the 20 sine of 354, and divide that by 30 degrees, sine of 30 degrees, I'll get the magnitude of C. So let me first put my Desmos in degree mode, create a fraction, negative 20 sine 354, so now it knows it's not a radian, over sine of 30. All right. So I got that value, it's about 4.2 miles an hour. Nearest integer, so 4 miles an hour. All right. So now from there, I need to determine the value of r, all right, the resultant velocity, which should be easy enough now. All right, I'm just going to clean this, make it look a little nicer. I like my notes clean. All right, so then I'm going to take this equation and I'm going to solve that for, well, it's already solved for r, right? So let's get a little fancy here. Let's call this A. So the magnitude of r, the resultant velocity, is going to be, instead of magnitude of C, I'm going to say A cosine 30, close it up, plus 20 cosine 354, close it up. And so now we have our resultant velocity. I'm just making sure I typed in everything correctly. I think so. So to the nearest Well, the first one was to the nearest integer. The other one it didn't say, so I'll just go to the nearest tenth. 23.5 miles per hour. All right. So number 2, Tabitha took a journey due north in a blimp. That's not what it says, but that's the idea. She traveled 45 miles per hour by setting a course 17 degrees west of due north. All right, so we got some things to work off of here. So here's due north. Here's something that's west of due north to compensate for a wind that was blowing 50 degrees east of due north. Just ballparking. What we've learned in some of the previous examples, if this thing wants to work, you know what, freehand, is that I'm going to need an x-axis that I'm going to call 0 degrees. All right, we'll draw a diagram and find the actual velocity of this wind-blown blimp to the nearest integer as it traveled due north. All right, so this is going to be the resultant. So that n is resultant. So I'm going to call this E, poor quality E. I'm going to call this E, and I'm going to call this W. I'm not going to go too crazy with the drawing of a parallelogram here. As long as we know that n is going to be E plus W, that's good enough. All right. 17 degrees west of due north. Off of the 0 degree mark, that's, well, 90 plus 17 is 107 degrees. 50 degrees east of due north. So 50 degrees back from the y-axis is going to leave us 40 degrees off of the x-axis. All right. Now, she traveled at 45 miles an hour by setting a course 17 degrees. So they're telling us that the magnitude of W is 45. We don't know the magnitude of E, and we don't know the magnitude of N, which for whatever reason I opted to make capital here. All right. So it looks like a similar problem to what we just did. So let's do E equal to the magnitude of E times cosine of 40 degrees, sine of 40 degrees. W is equal to, we know W is 45. Cosine of 107. Sine of 107. And N, well, we don't know its magnitude, but we do know that it's going off in the 90 degree direction. So cosine of 90, sine of 90. All right. So same idea as the previous question. I'm going to say the magnitude of E, cosine of 40, plus 45 cosine of 107 is going to be equal, cosine of 90 is equal to 0. Magnitude of anything times 0 is going to be 0. So I'm actually going to work with this first and say that the magnitude of E is equal to negative 45 cosine 107 degrees over cosine of 40. All right, so I'll do the whole A equals fraction negative 45, and you're like, negative? How are we going to get a reasonable velocity out of this? Well, cosine in the second quadrant is going to be negative anyway, so the two negatives will offset. So actually, you kind of needed it to be negative because the denominator is going to be positive because that's first quadrant. So we're looking at about 17 and change. Let's see, nearest integer. We'll use an approximate symbol. So that would be the wind, 17 miles an hour. Now we just got to figure out N. All right, so I'm going to do a little shrinky-dinky action here. and then come up with the second equation, which is going to involve the sine function. So we're looking at the magnitude of E, which we could put in right now, but I'm not going to. I'm just going to write up the equations first. 40 degrees plus 45 sine of 107. And then that's going to be equal to, well, we got sine of 90, which is 1, times the magnitude of n, which is just going to be the magnitude of n. So for consistency, I'm going to shrink this down a little bit. And you can see here, it's just going to be a matter of popping this into Desmos to get our n. Right? Because we already have the E stored in as A, if I can speak. Sine 40, A sine 40, plus 45 sine 107. Close them up, and we're talking, again, if we go to the nearest integer, we're talking 54 miles per hour. All right. She aimed her blimp at that angle west of due north, setting it for 45 miles an hour, but then she gained some velocity based off of the wind. All right, so she gained an extra 9 miles an hour out of the 17 miles an hour that the wind was providing in its direction. All right, so that's actually where